Okay. Hi, everyone. I'm Akiko Takeda, a team leader of Continuous Optimization team. And this is the term of research presentation of Continuous Optimization team today. So thank you for joining our seminar. And before moving to research presentation, I want to share some regulations. It's regulation notices about this seminar. So number one, reproduction is prohibited, and reproducing all or any part of the contents is prohibited without the author's permission. And this seminar will be recorded, and the video will be available on the Riken AIP website later. If you have any questions or comments, please scroll to the bottom of the page and click the Q&A tab. And you can put questions or comments in the box. So you can put your comments, questions anytime, even during the presentation time. I have a Q&A time after each talk. So yeah, we'll reply to the questions in the end of each talk. Is it okay? Yeah, as I introduced, I'm team leader of this research group. And okay, so today I want to talk about these topics, but not details of these topics because next two speakers, Tinshan and Mike, will talk about this related works about difference of convex approach for non-smooth, non-convex optimization problems. So I hope that my talk will provide basic knowledge to listen to the next two talks. All right. So yeah. So before moving on to the research topics, I want to introduce my team members. My group, Continuous Optimization Group, has 5 researchers: Okuno-san, Pierre, Mike, Tinshan, Jeff, and also visiting researcher, scientist, Tanaka-san. And yeah, and we are working on bit difficult problems that appear in machine learning, control, and operation research fields. And so especially we have research results in these topics, non-smooth, either and or non-convex optimization problems, bi-level programming problems, large-scale problems. Those problems are bit difficult problems. So it's I think it's good topics to work on. So that's why we are working now on these topics. But of course, we are not restricted to these topics. And yeah, we are always looking for interesting problems, approachable, and also it's nice if we want to provide some theoretical guarantee when we develop an algorithm. So yeah, we are working on such a problem. And now 3 members in these 5, among 5, 3 will leave soon in the end of this semester. All right. Okay, so I will explain the previous research topics. I explain in more details. For example, we developed efficient deterministic or stochastic algorithm for non-smooth, non-convex optimization problems. So non-smooth, non-convex, those keywords, those features make optimization problems a bit difficult. So, so we now working on either of these features, non-smooth or non-convex, or either or both features. We work on such a problems having non-smoothness and or non-convexity in our optimization problems. And we had some research results, and they are published in these papers. And also some of, still we are now in a submitting several papers in these topics. And so next two speakers will talk about a deterministic approach and also stochastic approach for these problems. And then Okuno-san will talk about these topics, bi-level programming. So we develop an algorithm for more general bi-level programming problems, having no smoothness in the lower level problem. So bi-level programming problem is formulated as follows. So objective function exists and the constraint part, another optimal optimization problem appears as a constraint. So in such a case, lower level problem in a constraint, the optimization problem in the constraint part, it is often assumed to have a smoothness condition because the lower level problem is replaced by the KKT condition in most cases. So that's why smoothness is important to replace the optimization problem by KKT conditions. But we gave an algorithm which allowed to have smoothness in the lower level problem. So Okuno-san will talk about this. And today, because of the time restriction, we cannot have present the research results, but we are working on this. So we try to reduce the problem size, having theoretical guarantee of the approximation gap from the original problem. So so this is called dimensionality reduction. So we are working on dimensionality reduction of optimization problems, and will provide a theoretical guarantee approximation gap from the original optimal value. So it is another research topics we are working on, but unfortunately today we have no enough time to explain it. But maybe if we have it next time, I want to explain this one. All right. So today, especially in my slot, I will explain these topics: non-smooth and non-convex optimization problem. All right. So okay, this is the problem we want to solve. So if L smooth function G0 to Gm are prox-friendly function, and this is defined as follows: prox-friendly proximal operator of Gi function Gi is defined as follows. It's an optimal solution of this problem. So we assume that this optimization problem can be solved easily, like a cross-form expression or n order n, a linear order, or log scale order or something. So yeah, we assume this one proximal friendly for G0 to Gm. And AI, it's a linear mapping. So this is our problem. And okay, so this is an example of our formulation. And suppose that we want to evaluate housing value using regressor. So it's a regression problem. And we suppose that we have matrix and vector A and B. And using those vectors matrix, we want to have a regressor that best fits to the given data set. And the data consists of M houses, and each data sample has these features: how old the building is, rooms, crime rate, etc. And suppose that we want to select important key critical data from the whole bunch of features, and using only critical data, we want to have a regressor. So this is the problem. And so nowadays we have lots of data set, but maybe there is only maybe 10 or 5 important features that give a big influence on this mission, housing estimation of housing value. So we want to select key, important, and k elements. So for the purpose, we can use L0 norm constraint like this. So L0 norm is defined as the number of non-zero elements in a vector W. So this is L0 norm constraint, and we want to select important k elements from the whole data set. So this is the problem we want to do, and sometimes we want to add additional constraints. For example, some weight need to be positive or negative. In this case, maybe the older building will decrease the value, housing value. So maybe this weight need to be negative value. So for the purpose, we can add a negative non-zero constraint for W1 like this. Or if the order is important, W1 is absolute value of W1 should be larger or equal to the absolute value of W2, for example, then we can add such a constraint in C. So anyway, we can make a problem setting more, realistic by introducing those constraints. And then this problem can be expressed as like this, using the indicator function. Two types of indicator functions. One indicator function is for sparse constraint, and the other one is for constraint C. So these things. So this problem has two terms like this. So in addition to G0, we can accept more terms. So we can express this one as in our formulation. So, and another example is like this. So this example looks like the same with the previous one if we ignore V, additional vector variable V. So because this V is corresponding to outlier detection part. So yeah, this example is for simultaneous sparse recovery and outlier detection. So because of this L0 norm constraint for W, we can do a sparse learning, sparse optimization as I explained in the previous slide. And by including one additional vector V, we can do outlier detection. So suppose we ignore this V, L0 norm constraint, then this optimal solution gives optimal value 0 because of V, all error residuals can be canceled out. So we want to restrict the number of non-zero element V, and if V becomes a non-zero value, then it means that it's corresponding to outlier. So real world data set sometimes contain outliers. It gives a huge residuals. So we can avoid those residuals because outlier is sometimes can be mistakenly included in A matrix A, B. So those things can be eliminated by including this vector V. And also we can control the number of outliers by using this L0 norm constraint. So in this case, two L0 norm constraints appear in one problem. So again, this is in our good example of our formulation. So we can deal with those problems by the formulation I showed before. Okay. And check the historical history of this area. So at first, this problem was studied by these researchers at age 2009, and they applied proximal gradient method for this problem. It is called IHT method. And after that, we added simple constraint. And now we could generalize up to here. So we allow more constraint in addition to L0 norm constraint. Like this. And now Tinshan apply this method to applications in control area. And also Mike made the stochastic variant of this algorithm for non-smooth, non-convex optimization problem. So they will talk about this research results later in this seminar. Okay, so let's look at the basic problem. So this problem is very simple, only one constraint, L0 norm constraint. And assumption is like this: f is L smooth function. And okay, so they Bloom, Sass, and Davis applied proximal gradient method for this problem. Then the method iteratively solve this problem in a teeth iteration. So this is a proximal operator for this indicator function of this constraint. And it is exactly the same with projection operator. So what we need to compute is to move the point to the steepest descent direction with the step size 1 over L. And then the point will move beyond from the constraint. So projection need to be done to satisfy this constraint. And then we can calculate next point. So this is a very simple procedure. And we can do this projection operator easily. So sort the absolute value of W from large to small, and keep the large K element as it is, and the remaining part should be replaced by 0. So this is a simple projection operator. So we can calculate this next point easily. And if we repeat this procedure, we'll have a stationary point of the problem. So, but weakness is, as I said, if there is one more constraint, it will destroy this algorithm and also theoretical guarantee. No, we need to think of a projection onto the intersection of this constraint and another one, C, at the same time. And it is, in general, difficult. So we need to think of another way of dealing with more constraints, more terms here. So yeah, because in general, as I said, if we can deal with this one, G0 plus up to GM, if we can deal with this proximal operator for G1, G0 plus G1 plus up to GM at the same time, by sequentially applying proximal operators, it's nice. But some sufficient condition holds, we can do it. But in general, it's not, equality does not hold. So we cannot use this strategy, even though each of term is proximal friendly, but altogether, it's difficult to calculate a proximal operator for whole red part. So it is one reason why this problem is difficult. And another reason is that this linear operator, AI, makes the problem difficult to deal with. So yeah, this one. Now, even if has a simple, easy proximal operator, GI tilde cannot have a simple operator in general. So it makes difficult. So this is two difficulty in this problem. And also we can change the sparse term L0 to different one. SCAD, MCP, LQ regularizer are also alternative regularizer that achieve sparsity of the solution. And they are proximal friendly, non-smooth, non-convex, sparse regularizer. LQ case is special only Q equals to this value. There is a cross-form proximal operator. But yeah, SCAD, MCP, L0, it has cross-forms expression. So, because their term is separable, the function is separable. So we only do calculation of optimization. It's enough to solve optimization having only one variable. And if we do this calculation for vector size, we can get a solution, a closed form solution. So yeah, so we can replace L0 pert by another one. And so yeah, so we can think of another type of sparse regularizer for G0, G1, and also AI is helpful to express structural sparsity like this. This regularizer often used in image processing because it can make small the horizontal and vertical differences between pixels. So in such a case, this regularizer is used with some linear operator. So yeah, and also we can think of a matrix version of this problem, matrix optimization problem, and we can think of these constraints all together if we want. I have no idea what kind of applications need such a constraint all together, but we can do it because we accept more than 2, 3 constraints here. Okay. And related works is like this. So far, these researchers worked on similar problems, but their problem setting assume G0 is non-convex. That's it. So, but no more terms. And stochastic case, Xi is a random variable, and stochastic approach try to solve this problem expressed with expectation in terms of Xi. And these researchers worked on this problem and provide a non-asymptotic convergence to the gradient mapping when G0 is convex. So there is a restriction. G0 is convex, but in our case, non-convex is acceptable. So that the extension from the previous works. Okay, and key idea of our research top algorithm is to replace this difficult part by a Morrow envelope function. So Morrow envelope function gives a lower bound for this function. And Morrow envelope is an optimal value of the same problem with a proximal operator. So proximal operator is the optimal solution of this problem, and Morrow envelope is the optimal value. So we can replace this part by Morrow envelope function. And it is known that Morrow envelope can be represented by two convex functions, convex minus convex function. And minus convex function is a concave function. So no, it's not still not convex function in whole together, but we can linearize this part because we know that gradient, subgradient vector of this part is can be obtained by the calculation of proximal operator. So proximal operator gives a subgradient belonging to this one. So we can calculate gradient vector by calculating proximal operator. And if lambda I goes to 0, this one goes to the original, close to the original function. So yeah, this is the example of Morrow envelope. And when we think of a LZL norm constraint, then this convex spurt is corresponding to this term, this norm. And this norm is defined as follows. Suppose that this W vector is the order from large value to small value. And this one is the sum of large K elements. And so notice that this constraint is equivalent to this one, because this left-hand side means that the summation of the remaining part. So this summation need to be 0, mean that this non-zero element, number of non-zero element need to be less than or equal to K. So it's equivalent. And you find that Morrow envelope is something like penalty function for this constraint. So yeah, lambda is like a penalty parameter in that sense. And yeah, penalty parameter becomes small, large, then it looks like a constraint, original constraint, also known constraint. And yeah, our algorithm is something like this. So we replace this complicated term by Morrow envelope and split into two-part, convex minus convex part. Minus convex part is a difficult part, but yeah, but it is linearized sequential. So our algorithm consists of two loops: outer loop, degrees lambda and epsilon, and inner loop we calculate epsilon stationary point for this problem. And this concave part is linearized, but this convex subproblem has a closed form expression. So we repeat this procedure until termination criteria with epsilon are satisfied. And then sequence, we got a sequence that goes to W star, and accumulation point W star satisfy the first order optimality condition of the original problem. So this is theoretical guarantee. And yeah, and this convex subproblem can be obtained easily by as I said, linearization is easy. And yeah, and what we need to do is to solve this problem. But this problem is equivalently represented like this. And this blue part, this parenthesis already have constant vector. And prox operator is applied to the fixed vector and get the next point. So we repeat this procedure by changing, in our loop, we repeat the procedure until convergence. And after that, lambda epsilon are changed. So we repeat this procedure until lambda epsilon become almost 0. So this is the approach we took. And sorry, I have not enough time to finish this presentation. And stochastic setting is represented like this, or finite sum case. M is a super large size. So we want to select some of them because we do not want to get gradient computation for whole M samples. So yeah, we can think of a stochastic approach for the problem. And Mike will explain stochastic proximal gradient method for non-smooth non-convex problem. And Tinshan will show the application of the algorithm I explained to the problem having multiple run constraints. And Okuno-san will talk about bilabial non-smooth optimization methods. That's the end of my talk, and go to the question time. And so any questions, further questions, comments? If not, then yeah, move to another. I want to move to another speaker. And Tianxiang, are you ready?
Hello, everyone. This is Tianxiang Liu from Continuous Optimization team. So following Takeda-sensei's talk, I will introduce an application of the so-called SDCAM method to no-rank problems. This is a journal work with Takeda-sensei and Tinky Pong, my previous mentor in Hong Kong, and a professor in control area, Ivan Markovsky. So first, we look at the problem, which comes from a linear time invariant system identification. So this is a problem in control area. And this problem, the goal of the problem is to minimize loss function f, which is supposed to be Lipschitz continuous for the gradient. And the loss function here normally represents some measurement between the noisy signals and the true signals. And the constraints we have multiple low rank constraints. So in total, we have n+1 constraints. The first capital N constraints are separable with respect to each variable yi. It belongs to Rn, while the last constraint is a coupling constraint with respect to y1, y2, yn, all the variables. So here, you may have noticed that inside the ring, there is like HRI plus 1 or HR plus 1. So here, this H something with a matrix is the so-called Hankel matrix, which has this kind of a structure. So it is a special structured linear mapping to this variable to get a rank, and this rank get a matrix, and this matrix has no rank structure. And also there are some parameters for the ranks Ri and R basically satisfy this condition. This basically requires all the rank, all the matrix we have is are the fat and the short matrix. So this problem is definitely difficult to solve because even though we don't have a Hankel structure inside, it is difficult to solve because especially the last coupling constraint. So for example, the all kinds proximal gradient methods cannot be used to solve this problem because the most difficulty lays in that the projection to the fitable set is definitely impossible. So to solve this problem, we want to make things simple. So we have multiple constraints. So what if we can reduce some of the constraints to keep just one constraint or just nothing below in the downstairs? So the intuitive way to do that is to use the penalty method. So before using penalty method, we write this problem as a uniform reformulation, which looks like an unconstrained problem because every constrained problem can be written as an unconstrained problem if we allow some parameter to be like an indicator function. That means that if y, for example, this indicator function means that so if y belongs to this set omega, then this function value is 0. But outside of omega, the objective the value is infinity. So we have basically several kinds of reformulation of the original problem to be an unconstrained problem. So first type, for example, we let this omega to be the feasible set of the first n constraints. But we write the other part, the last constraint in this part. And the second type is that we do the opposite. So this omega represents the feasible set of the last constraint, but we write the other parts, the first constraint here. And of course, we can do everything we put all the parts in here, and we keep this omega to the whole space. So basically here, omega means that if we solve this problem, we keep this omega in the constraints, no change, but we parallelize some part related to these terms. So we have three kinds for formulation like that. So as Takada-sensei just mentioned, this is basically looks very like the formulation of the problem solved by SDCM problem, because you see there's some final summation of these terms, and each term inside is a linear map, and outside is like an indicator function. But this indicator function basically is Prox friendly, because the proximal operator of the indicator function basically corresponding to projection to this set. So you see this all this set is like a lowering constraint of this. So you know that the projection to this set will give you a closed form solution if you do SVD decomposition. So we would like to use the SDCM to solve this uniform reformulation, which of course contains three kinds of specific reformulations. And so the idea of SDCM is to, based on observation that the more envelope function of the P function, which is written like this, it can be written as a DC decomposition, means that the difference of two convex functions. So this is quadratic convex function, and this is also convex function. And more importantly, we know that the subgradient of this term, convex function, can be obtained by doing projection to the no-rank constraint. So the SDCM applied to this uniform formulation written here could be, sorry. Okay. So could be solved the corresponding F lambda. So F lambda is an approximation of the original objective F by replacing all these functions, each of these function, indicator function, by their corresponding Moore envelope functions. Then if using this Moore envelope that has DC decomposition, we can further write this Moore envelope function as the DC part, the concave part of the DC function, and the concave part of the DC function here. So the corresponding approximated function F lambda will have a good structure, because you see like F is smooth. We suppose not function is smooth, and this is also smooth. And this part is a summation of multiple of these parts. We know that the subgradient of each part can be obtained easily. So we can also get a subgradient of this part. So basically, SDCM is to successively minimize this F lambda, and by decreasing lambda, thus to get an approximate solution of the original objective. So now the subproblem of SDCM is to solve this problem with a fixed lambda, right? So that's to subproblem of SDCM is to minimize H plus this indicator function minus this G, whose subgradient can be obtained. It's like that. So this is a subproblem of SDCM. So to solve this problem, we can make use of the structure. So like, for example, there are many variants, but we can take one of them, like the MPG major, which is to majorize this part in the subproblem and to use a non-monotone proximal gradient to the other parts. So basically, the subproblem MPG major applied to this problem, we have this kind of subproblem. So that would be like we choose subgradient at a given iterates at CL, and we approximate this by linearization, this term. And we also approximate this term by linearization and with this quadratic term. And we keep this non-smooth term. So basically, the subproblem will become a projection problem. So that is, so now our goal is to solve this projection problem. We need to do projection to this omega. And as you can see, if you remember, we have three kinds of formulation. So for the last type 3, this omega is the whole space. So the projection is fine, it itself. But for the type 1 and type 2, our omega, we have this kind of looking. So this is still hard to do projection, because especially there's like a Hankel structure inside. And this type 2 will correspond to just one constraint, but type 1 will correspond to the inseparable constraint, which can be written as just respect to just one constraint, because they are separable respect to the variable. So basically, we need to do projection to some constraint like a rank and something inside the Hankel structure and bounded by some rank, this kind of thing. So, this is difficult. We couldn't get that. And now we are thinking if that we do not use a true projection. So we are thinking that if it's possible, we use some approximate projection, which is available to replace this true projection to the subproblem, that we can still get some like a good performance with the theoretical guarantee. So to this goal, we propose the so-called pseudo-projection. So pseudo-projection introduce a reference point U in the set to do projection. So it is defined as this set. So this shows like the pseudo projection of the point y hat to the omega, the set omega with a reference point U. So this corresponding to the set of that each y satisfies two conditions. So the first condition corresponding to some like optimatic condition, a stationarity condition, which is also necessary for the true projection. And the second requirement is that we don't allow the point in this pseudo projection set to be the shortest distance, but instead that we require that the point to the y hat, which needs to do projection, should be a bit shorter or not larger than the distance with the reference point with this point. So something like we relax some relaxed condition of the true projection. So the pseudo projection can be regarded as an extension of the true projection. So that's to say every point in the true projection will also falls into the pseudo projection set. And later in this section, we will introduce how to implement the pseudo projection. But now we just use this pseudo projection framework instead of the true projection framework. So as you can see, our subproblem, the MPG major will be like a projection to this omega, but instead we use like a pseudo projection to replace that. And we get a new algorithm, the so-called variant of MPG major. So now somehow in this framework, we solve the issue for the projection using the pseudo-projection. But there is another issue we need to do, we need to solve. That is, we couldn't solve the original problem by SDCM itself only, because if we our lambda goes to very small, then the computation cost will be very high. So that's the reason why we introduce some like post-processing after we obtain some approximate solution by a relative not too small lambda. So then, and this is the also the motivation that we want to get a good a solution with very good feasibility, because it's very important in system identification. So in after solving the problem by SDCM until some threshold lambda bar, we switch the algorithm to post-processing, which is like very simple, like alternating, but pseudo projection, not true projection, because we still couldn't get the true projection. So this omega 1 represents the first, the physical set of first constraints, and omega 2 represents last physical set of last constraint. So after we obtain some relatively good solution, we do alternating pseudo projection to these two sets, thus expect to achieve a solution with with better feasibility. Well, we don't need so much computational cost. So to summarize, what we have done is to this hybrid method. So our original problem can be written as this uniform reformulation. Then the hybrid method, we include the SDCM and also the post-processing. So the SDCM, basically, we first pick some decreasing parameter, lambda t, and some threshold of this lambda bar. And we fix every lambda t, we minimize f lambda t instead of minimizing fy. So it's by the V-MPG measure we just mentioned, whose subproblem is pseudo-projection. And then we decrease lambda t, and we successively minimize f lambda ty, and in the outer loop, we get a sequence yt. So if this lambda t is smaller than some lambda t bar is smaller than this threshold, we just switch SDCM to post-processing, and we use approximate solution as an initial point for this post-processing, and that's to do alternating pseudo-projection. So next, I will introduce a theoretical guarantee we can obtain from this hybrid method. So first, I will introduce the convergence of the SDCM part, the first part. So suppose that we don't switch to the later part, we will obtain infinite many of the sequence iterates yt. Then we can show that this yt, the sequence is bounded. And then we have at least a combination point, right? So we show that any accumulation point will be also a feasible point of the original problem. And also, moreover, if this feasible, if the accumulation point satisfy this kind of CQ, and then it will be a station point of our original problem. And this CQ will be satisfied by some special cases. For example, we for some, how do you say? So for all the regularizers, if one of them, at most one of them are not locally Lipschitz, then the CQ will be satisfied. So we also have this result about the constraint violation. So that shows that our constraint will be like y belongs to some ci. So the distance shows some kind of violation of constraint, which could be bounded by this term. And this term includes this lambda t minus 1. So somehow like if we don't switch to the post-processing, we just solve it by SDCM, then in decrease this lambda go to 0, then finally theoretically we can get a feasible solution. This is something also shown here. A combination point is feasible. And also for the post-processing, we also have some theoretical result. So the sequence xt and zt will be they are the sequence generated by the post-processing scheme. So like xt, zt, we do alternating pseudo-projection. And for this sequence, under some condition, the sequence will converge to a feasible point, which is omega 1 intersects with omega 2 with R linear rate. So, and this condition, basically there are two conditions. So the second condition is very standard condition, even though it's hard to check, but it's very standard condition, almost in every paper who establish convergence rate. This is necessary. And this first condition, which can be checked, and we can show that indeed it could be satisfied. So, okay, now we go, as we mentioned before, now we go to see how to implement the pseudo-projection. Yeah, because we give a framework of pseudo-projection in the algorithm framework, but we don't know how to realize, how to implement this pseudo-projection. So this part, I will introduce a realization of the pseudo-projection. So all the pseudo-projection in the previous problem basically contains these two kinds of set defined by these constraints. So this is the first n constraints, this is last constraints. So basically this can be written as a uniform formulation like a ring of a linear function, and this bounded by some m. And our goal is to get a pseudo-projection to this uniform set with, for example, given some point and with some reference point. So the tool we use is some like existing solver called LRA. So it's like a structured null ring approximation is an existing solver. So the key of this solver is to equivalently writing this constraint as the existence of some is row vector, such that this vector is the left kernel of this matrix. So here is 1 because when the difference is basically this number should be the difference of this term minus this term. So in every case it's like R plus the difference. So in these two cases is 1. So that makes the equivalent problem we have just vector. And the procedure of the SLRA is basically to first to define auxiliary problem with respect to this R, and then solve this problem with this orthogonal constraints, and then take this solution R star back to this original projection problem, thus to get the Y star. So basically, if this in our problem this is 1, because then this R problem will be very easy to solve because it's just a vector problem. And then basically we only need to solve this projection problem, but this is easy. It has closed form because this project is Y hat. to this space. And we show that this is defined phi, and I mean the R problem, objective of the R problem is smooth. So we have all kinds of classical methods for this problem. And we need to show that indeed by doing that we obtain a solution which will be our point in our pseudo projection, right? So we need to check two conditions for pseudo projection. The first condition is that we need to show some like stationality. So this theorem tells us under some condition we show that the R star obtained by this way will be a stationary port, which it means that it satisfies the first condition of pseudo projection. And this other result shows that this point will satisfy the second condition of the pseudo projection. That is a relatively distance decreasing with respect to the reference point. So until now, we have done the framework and we have done the pseudo projections of problem. So now I would like to just briefly show the numerical experiment results. So we consider the problem with two variables, and we have some data setting, and we have this kind of numerical results. So first, for different group, the rank group, so 222 and 264. This shows the termination function value, the average termination function value over maybe 10 or 20 random seeds we obtained by our three hybrid method. So we have three reformulation, so correspond to these three method. And this AP means that we solve this problem by alternating pseudo projection. In the beginning, we don't do SDCM to get an approximate solution. So as you can see that indeed we need to get an approximate solution by SDCM, say SDCM, thus we can get a better result, the same. And we also show that the constraint violation before and after post-processing. So for hybrid method 1, this is before post-processing, and after is the same, similar. So that shows the necessity to do post-processing, because after post-processing, we indeed get a solution which have better feasibility. And we also compared our three hybrid method of with respect to CPU time. So as you can see, so normally the second type of reformulation, it will give you a hybrid method, which is much faster than the other two. So, okay, so I think I can conclude the talk now. So basically we introduce a hybrid method, which includes SDCM, and then post-processing, which is alternating pseudo projection. And also show the convergence for the first part, SDCM, and also the convergence rate for the post-processing part. And then moreover, we demonstrate how to obtain pseudo projection by existing solver and get some results guarantee. So all the content in the talk can be found in these two papers. So I think this is the end of my talk. Thank you so much.
Any questions, comments? So thank you, Tinshan, and yeah, let's move to next speaker, Mike. Yes. If you are ready, you may start anytime.
Let's begin. So the title of my talk here is Stochastic Proximal Methods for Non-Smooth, Non-Convex, Constrained, Sparse Optimization. So the general problem setting that we're interested in has this following form, a sum of 3 functions. So the next few slides, I'll try to motivate why we're interested in this specific class of function. So the first function f, we assume it has a Lipschitz continuous gradient. And this would be, I guess, considered the true objective function of our problem, what we're really interested in. So this would be, for example, a loss function in machine learning. And we don't assume this function to be convex. In addition, we assume this function f takes the form of an expectation of a stochastic function capital F, where C is a random variable that we can sample from easily. And we mostly work in this more general setting, but probably a more familiar setting would be a finite sum problem, where we have, let's say, n sample points. So in like machine learning, we'd have some x and y. X is the predictors, and y is the output we're trying to predict. So this is all just encased in this C random variable. And so each of these smaller functions fj, this represents our loss function evaluated at each of these data points. Okay. So the second function g, we just really assume that it's Lipschitz continuous, and this acts as a sparse regularizer. So this has been discussed a lot already, but mostly we want to avoid overfitting. So we don't assume this function to be smooth nor convex, but we do assume that it has an easily computable proximal operator. So we were able to minimize this function inside the curly brackets, and or at least get a minimizer of this function within the curly brackets. So we're trying to minimize g while staying close to the argument w. And so there's many popular regularizers that fit this criteria, such as MCP, SCAD, log sum penalty, etc., that we can find in machine learning and statistics. So here's just one example, and I guess I think Takeda Sensei explained this well already. So, but basically, with this non-convexity, we're able to get a much better refined penalty of W, our solution in each dimension. We're able to basically penalize non-zero values much more accurately than, say, a convex regularizer. And so finally, we have this function h, which we just assume to be a proper closed convex function. And so our motivation for this is mostly to be able to handle some set of constraints. So really, we have this constraint set C, which is closed convex. And so we can add this function h, which really only allows our solution to be feasible within this set C. So if it's outside the set C, we get this infinite penalty. And the main assumption here is that this projection can be done easily. So one sort of simple, concrete example or application that fits our criteria exactly would be non-negative sparse principal component analysis. So this quadratic here would be F. And so we see this is non-convex, it's concave, and but smooth. And so G could be one of the previous mentioned regularizers. And then H could be formed for this convex set C. Basically these constraints here, and this has a closed form projection. Okay. So now sort of explaining the application or the problem setting, we'll look a bit more into the optimization side using first order stochastic methods and sort of look at a little bit of the history of some of the main algorithms for simpler problem settings. So just to begin, we'll consider just minimizing F. So I think it's well known, the most popular, you could say the most popular algorithm for training machine learning models is stochastic gradient descent. And so here, this is a mini batch setting where we've taken M samples, and then we approximate the gradient of little f by taking this average over these samples of the stochastic functions gradient, and then move in the negative direction. So a key assumption is that we can generate unbiased samples of the true gradient. So assuming this expectation of the gradient of the stochastic function equals the gradient of the function little f, then we're moving in the direction of steepest descent in expectation. So especially in non-convex optimization, I think an important aspect of the research is properly defining your convergence criteria, because unlike in convex optimization, we can't really hope to find a global minimum. So in the non-convex setting, there's many local minima. So let's say in the deterministic setting, we would want to try to find a stationary point. And in this stochastic setting, we'd want to find an expectation approximate stationary point, or most of the work considers developing an algorithm and giving a convergence rate to ensure a small level of error, epsilon. So we want to design algorithms which guarantee after we can give an upper bound on how much computational power or how many iterations is required to ensure that in expectation, the norm of the gradient is less than or equal to epsilon. So I believe the first algorithm that proved a convergence rate is the work by Godemi and Lan in 2013. And so, and this is just not the mini batch, just the single sample SGD. And I guess a key, I guess for stochastic algorithms, it's maybe overly ambitious to try and give some sort of convergent guarantee for the absolute last iterate of your algorithm because of the randomness. So what's typically done is proving some convergence rate for if we look at all the iterates and we sort of on average what's their performance. So another way to do this is basically if we give an upper bound on the number of iterations we want to do, then we could run the algorithm for n iterations, and then we can say something about you can't really see my hand. We run for n iterations, and then we can make some sort of guarantee if we pick an iterate at random. So sort of this average performance. And perhaps a simpler way to represent this is to pick an upper bound in the iterations, and then we can uniformly sample over n, and then run for this r iterations, and then we can give a guarantee on WR. And so this is just the algorithm again. So the sort of general idea of this is if we analyze this algorithm and study the worst case performance in each iteration, we can get some sort of bound on the sum of the expected squared norm of the gradient of f, and it's moving, or it's increasing at a rate of square root of n. So that's not very good. But this is where this averaging comes in that if we consider now the rth iterate and we've uniformly picked it over 1 to n, then its expected value would just be this quantity divided by n. And so we're able to achieve this 1 over square root convergence rate. Okay, so that's a SGD for randomizing F. Now there's another important development is variance reduced methods. And this is not really talked about in papers, and this is not really what I'm going to explain here. Not really part of, not really a tool I've seen ever used in proving convergence algorithms, but I think it gives some sort of good intuition why they could be useful. So, I mean, the first time I saw these type of algorithms, I thought about this controlled variance and Monte Carlo methods, if anyone's familiar with that. But if we just consider, for simplicity, this finite sum problem, and we assume that n is not so big so that we could compute a full gradient if we want to. So we could really do gradient descent, but we can actually do something better than gradient descent, even if we can compute a full gradient by using a stochastic method and then improve it even more with a variance reduced method. So let's just say we have one iterate, it's called W1, and we compute a full gradient. Now we consider another iterate or another value of W, and we compute a stochastic gradient by just picking J uniformly between 1 and n, and then evaluating the gradient of this subfunction. So this is a stochastic estimate of the gradient, and it's an unbiased estimate, so its expected value will equal the gradient of f. Now, in the SGD update, we would just typically use the gradient of fj and move in this direction. But if we move in this direction, inside the expectation operator here, this is still, so instead of just moving in this direction, we move in this direction. So the gradient fj w1 minus gradient f, this thing. This is still an unbiased estimate of the gradient of w2, because these terms sort of cancel out, or the expectation of this equals this, and so this cancels out. Now the important thing is, if we look at the variance, we compute the variance of this gradient estimate. We get this -2 times the covariance of these two random variables, these two stochastic gradients at W1, W2. And so if the variance of, if this quantity is less than this quantity, we'll be able to achieve some variance reduction. And so then intuitively, if we're running SGD, and W, we have one iterate and one iterate not too far away, likely this stochastic gradient is correlated if we're using the same J. So if we're overestimating at W1, probably overestimating at W2, and is sort of adding these two terms helps to dampen the error. Okay, so that's some intuition. So this is so some variance reduction for stochastic methods. It's first achieved by Reddy and others. And okay, so this is a bit more complicated, but we can just, all these details are not so important. So we just have an outer loop 4K and an inner loop 4T. So basically every outer loop, we're updating this W tilde K plus 1. And then we're computing a full gradient. And then we're using this full gradient and this WK inside this inner loop, and are just doing what I was explaining before. So every once in a while, we compute a full gradient, and then we're doing just a single sample SGD in this inner loop, and we can achieve, in the end, a better computational complexity for achieving an epsilon stationary point. Okay, so okay, so now we're moving on to F plus H. So so F is Lipschitz continuous gradient, H is convex. So this is a very classic model, and lots of research done on this. So probably the most popular method is proximal stochastic gradient method. So in this setting, basically inside these brackets here, so V is just, we can just consider this as stochastic, the gradient of this stochastic function. So we're doing a SGD step. So we're trying to minimize F. And then given this update of SGD, we then want to minimize H. So we sort of do a step to do SGD, and then staying close to this update, we want to minimize H. So it's sort of alternating between minimizing F and H and going back and forth. And yeah, that's the idea. And so in this setting, popular convergence measure is basically making the expected norm of the gradient mapping small. So the gradient mapping is this quantity inside of the norm here. And so we want to develop an algorithm that can guarantee that this quantity is less or equal to some chosen epsilon. So some motivation for this. So this gradient mapping, why is this important? So if we look at the proximal gradient method, and we just add, subtract WK and multiply, divide by gamma, we see this looks a lot like a gradient or some sort of first order, looks like a gradient descent method with some sort of weird gradient estimate. But from looking at this, if we make this quantity small, then our updates are getting small. So basically we're converging. If we can make this amount small, then every iteration we're not updating W much. But more rigorously, we can show that if this gradient mapping equals 0, then in fact we found a stationary point for the problem. So this motivates this convergence measure. Okay, so for this problem, yeah, it's been a very quite active research area, and so this gives an opportunity to explain a bit more about sort of the objective here. So it's a couple papers, and we can see here, given there's a lot of flexibility on, say, how many stochastic samples you use every iteration, even in a finite sum case, you could potentially do a gradient descent, and then each iteration would be very computationally expensive. So the most important measure for the computational complexity is the number of gradient calls. So the number of times we have to compute the stochastic gradient. And because this is seen as the most computational heavy component of these algorithms. And so these are some convergence results. So as epsilon gets smaller, we were going to require more. And also another measure could be the number of times you have to compute the proximal operator. And this matches, this is sort of the same order of the number of iterations. Okay, so now we've finally arrived at the problem that we're interested in, phi. And so, yeah, I guess the initial part of this problem was how to measure what's our convergence criteria going to be? Because especially this type of problem with the three functions, 2 are non-differentiable, 2 are non-convex. There's not very good differentiation rules. And so our choice was to sort of generalize the gradient mapping to the sub-differential mapping. So previously the gradient mapping, this S would just be the gradient of F, but now given the non-differentiability of G, we're considering this set italic G phi gamma W. And so then our convergence criteria would be that the distance of this set G from 0 should be small. And in a similar way, we can show that when in fact this distance equals 0, we have some sort of approximate stationary point. So I want to mention that in general, the sum of the subgradients or the sum of the subdifferentials of each function is not equal to the subdifferential of the sum of the functions. But we can call this some sort of generalized stationary point. Okay. So now is some sort of ideas of how we analyzed our algorithm, or how we tried to develop the algorithm. So the first thing we did, we look at phi, we replaced the G in 5 with E lambda of G, which is the Moreau envelope. So this is now wanting the actual minimum of this function inside of the curly brackets. And as sort of mentioned already, I think the Moreau envelope is a lower bound on the function. So this gives a type of lower bound on phi. But using the current using the current iterate WK, we can construct a smooth majorizing function of f plus the Moreau envelope of G, which we call big EK lambda W. And it's actual, what this E is not, looks like, it's not so important for us. What's most important is what its gradient is. And so the gradient of E has this form. And so comparing this to the gradient of F, it's not very much more to compute the gradient of E, given by our assumptions that the proximal operator is easy to compute. So we just have to add do this prox operator and add this sort of simple term. And now we have a gradient of some smooth majorizing function of F plus E. So now we've returned back to a smooth function plus a non-differentiable convex function. So we've sort of returned back to just having two functions, a smooth and a convex one. But the one element maybe of a bit of difficulty is that this function E is not constant. It's actually dependent on WK. So this function is actually, we're minimizing a function that's changing each iterate. But one thing to note. So I won't go really into too many details on our analysis, but the general idea was, okay, we have this, sort of changing smooth function, but we were able to handle this. And so we first want to minimize the norm of the gradient mapping of capital E. So first, in our analysis, we want to minimize E, basically this function here, E plus H. So we minimize, we get a bound on the norm of the gradient mapping for this approximate function. So we can make this as small as we want. So this could be sort of epsilon over 2, let's say. And then basically so this is where the Lipschitz continuity of G comes in. So Lipschitz continuous functions and their Moreau envelopes have some nice properties that we could use. And then also something to note, we have a gamma bar and gamma. So there's some properties we could use evaluating the gradient mapping at different values of gamma. And with these two tools, we're able to bound the difference of what we are actually interested in. So this is the subdifferential mapping of phi and this quantity, basically the norm of the gradient mapping of the approximate function. We can make this as small as we want. So simply put, we could develop an algorithm to make this less than or equal to epsilon over 2, make this epsilon over 2, and then we can prove that this distance is less than or equal to epsilon in expectation. So that's sort of the general idea. Okay, so with that, I just show the algorithm. So compared to the algorithm of Demi and Lon, not so much was required to be changed. We have to just compute this proximal operator every iterate, and we incorporate more samples. So we take a mini batch, and we have to add this term, which is basically the gradient of the Moreau envelope of G. And then we apply this proximal operator to minimize H. So we do this sort of SGD, generalized SGD step to minimize F plus the Moreau envelope of G, and then we after that, we minimize, take a step to minimize H. And similarly, this variance reduced method, same thing. So I mean, we just had to do some minor changes here. So we just, again, the prox operator, adding this term, and then taking the prox of H compared to the algorithm of Reddy. Okay. And so there's really no other algorithms that we're aware of that consider this problem. So there's nothing really to compare with for in terms of convergence complexity for a stochastic algorithm, but we're able to prove these convergence complexities for a what we call an epsilon accurate solution. So the expected distance of the subdifferential mapping. So we require this order of gradient calls to get to guarantee that it's less than or equal to epsilon and this number of proximal operators. And so we did some numerical experiments. So we compared to a deterministic algorithm, SD-CAM, and yeah, this problem was discussed in the previous paper, but it has asymptotic convergence results, and but you can maybe tackle more general problems. But just for sort of proof of concept, we compare with this, and we did the negative PCA setting. And something to note, at least, so we didn't really tune the algorithms. We used the parameter settings which guarantee the actual convergence results that we proved. And for variance reduced methods, generally step size is smaller. So there's some sort of variance reduced methods. They have a better convergence complexity, but maybe in practice, unless the step size can be increased, maybe in terms of computation time, have a bit slower convergence. So we tried basically the step size used for the mini batch algorithm. We applied that step size for the variance reduced as well, just to see. And so we get this type of output for MNIST. And so this problem is actually a little bit simple. I mean, this other problem is a bit more interesting. RCV1 data sets, it's a larger data set. And but in both cases, this mini batch problem, this simpler algorithm, it worked better. But we see that that we get some sort of convergence. And that's the end of my talk. Thank you.
Okay. Thank you, Mike. And any question, comments? Okay. So yeah, so far it seems okay. So if you have questions, please.
Oh, there's one question.
Oh, really? Okay. So please.
What is the contribution of the Lipschitz continuous gradient? Yeah, this is I guess crucial for proving the convergence of the algorithm, because you can sort of bound the difference of the function values iterates. There's just a key inequality that that enables the analysis of this of these algorithms, and so you end up with some sort of quadratic term though of the gradient squared. So that's where the mini batching comes in. With the mini batching, we could make this quadratic term small. But yeah, we have some other work that is looking at not using this Lipschitz continuous gradient exam condition, but just sort of Lipschitz continuity. But it's a pretty standard, especially with non-convex problems. So I guess you sort of need something to work with. So if you don't have convexity, you know, you need something else to work with. Yeah, I don't know. It's not really really talked about too much, but yeah, there's usually some assumption that let's say like the expected I think norm squared of the true gradient minus the stochastic gradient is bounded by some sigma squared.
Oh, sorry, I noticed that 3 questions came to you.
Oh, okay. Oh, there's some more. Yeah.
Oh.
Okay. The numerical sparse. How the mini batch size. Yeah. Maybe just pull up the paper. So the mini batch size was chosen. Yeah. I just have this. Let me just see here. Let me just. If I can pull up. Yeah. I sort of. Let's see full screen. There's some. Yeah. It's determined really by. Let's see, it's really determined by ensuring the convergence. So for this, let's see here, where the, okay, so, okay, so we need alpha basically to be 2/3, and it's theta to be 1/3. Okay, so let's go back to the algorithm. So this, so yeah, we pick some upper bound on n, and then we choose m. This is the mini batch size, n to the alpha. So it's a quite large, we could say a fairly large mini batch size. And theta, yeah, theta determines the step size. So I think theta I said was 1/3. So so the step size, and we didn't do any tuning or anything. We just used sort of the settings that are that we can use to sort of optimize the convergence complexities. And how do you apply your methods? Do you apply? Yeah, we have a few examples. So there's physical problems like physics. I don't know about physics, but we had the non-negative sparse PCA, and so we did some sparse binary classification with outlier detection and fairness constraints. So that would just be binary classification. And then I think we did some, yeah, portfolio optimization. So some financial application, but I just sort of showed the simplest application just to put this into perspective. Yeah, I just showed this application, but yeah, we had a few different ones, but yeah.
Okay, thank you, Mike. And all right, so time is running out. So yeah, okay, good. Okuno-san, are you ready?
Sure.
Okay, let's start my talk. So the title is Hyperparameter Learning for Non-Convex LQ Regularizer. So via bi-level non-smooth optimization. So this is a joint work with Professor Akiko Takeda and the 2 students, so Kawara-san and Watanabe-san. Okay. And this is the outline of this talk. So first, so I explain the problem setting. So as well as the 2 previous talks by Mike and Tinshan. So this talks also considers a sparse optimization problem. So like this. And here, so G is a loss function. So this is added. So this is used for getting a good W that fits a given data. And RW is a sparse regularizer, which should be an approximation to the 0 norm. So that is a number of the non-zero components for W. Okay, and so this is so added to the GW, so as to get W with as many 0 components as possible. So according to the so-called Occam's razor idea that the number of the critical components should be small. And lambda is a hyperparameter. This is a key key notion of our this talk. And so differently from the two previous talk by Mike and Tinshan, so our research interest is to how to tune this hyperparameter lambda. So not solving this problem as it is, okay? And in this talk, so we consider how to tune this hyperparameter lambda for the particular problem like this, okay? And so this problem is this problem is featured by this LQ regularizer. And LQ regularizer, so WQQ, is defined like this. So summation of the absolute value of the each component of the time, so powers Q, and Q is less than 1. Okay, and so G and the other regularizers are assumed to be a C2 function, that is twice continuous differentiable function. So because of some technical reason, the point is that this term, okay? And so let me explain this term a bit. And this is a so-called bridge regularizer. And so this is a figure of the graph with one dimension, okay? And so from this figure, you can see this function. So this function is non-smooth and non-convex, okay? And unfortunately, so this function does not satisfy the local Lipschitz property at W, so which has a 0 components like this, okay? Okay, so next, so I explain the example of this problem. So I want to give some specific forms of G. So as an example of the loss function G, so assumed to be the C2 functions. So we consider the L2 loss function for regression and a logistic loss function for classification like this. And the regularization part. So example of this is a single LQ regularizer. Okay. And so another one is the elastic net type regularizer. So this is a modification from the pure elastic net regularizer using the L1 norm. Okay. Okay. So this problem is regarded as very important for many researchers. So because there are some applications such as a matrix compression and denoising, compressing sensing, and the CT reconstruction. And so for such important applications, so there are so many algorithms. So for example, smoothing type methods, so combined with popular algorithms such as SQP methods and the interior point method, and so on. So these algorithms suppose the hyperparameter lambda are prefixed. Okay, so lambda is a prefix. So these algorithms are developed. So assuming lambda is previously given. Okay, so of course, so depending on the choice of the hyperparameter lambda here, so solution of this kind of the problem is different. So as a result, so constructed model using the different lambda performs differently. So there is a natural question. So how to tune? So how to select a good value lambda? Okay. So one common methodology in machine learning area is as follows. So suppose that we are given a data set. Then, so we divide this data set into the 3 kinds of the set: train set, validation set, and test set. So we construct a loss function using the train data. And for variance lambda, we solve this problem. And to get its solution, say W lambda. Then we next. So using the information of the W lambda for various kinds of the lambda, so we find lambda. So that gives the best fit to the validation data here. So test set is so used for final checking the quality of the output solution W. Okay. Okay. So next, so I explain so this procedure more precisely. Okay. So for explanation, so I define some functions. So let GTR be a loss function. So construct using a training set, and G-bar be a loss function using the validation set. Okay. So example of these functions. Sorry, I forget. So GT function is so also defined. So using the test set. Okay. And this is an example. So consider that we want to solve the linear regression problem like this. Then we are first given the data matrix and the vector A and B. Then we divide the three parts. So like this, A bar, AT, ATE. Then so in this case, so three functions are defined like this. Okay. So this is an example. Okay, so using these two functions, GTR, G bar, we construct the following the program here. And we select the best lambda by solving this problem. Okay, so this program minimizes F lambda with respect to the lambda non-negative, and F lambda is defined like this. Okay, and so the point is W lambda. So W lambda is a solution of this problem. So this problem is a GTR function, and this one is a regularizer. Sorry, so R1 is assumed to be a LQ regularizer. Okay. Okay. So, but this problem is still very difficult problem. So popular methods are using the grid search and the Bayesian optimization. So grid search, okay. So grid search is finding a best lambda. So best lambda, so which attains the optimal F lambda. Okay. So among the grids, so placed over the prefixed region. And the Bayesian optimization is also a very popular optimization methodologies, which is based on the Gaussian process. So this research, so we don't take these two approaches. So our approach is based on the bilevel optimization problem. Okay. So in our approach, we regard this problem as the following bilevel optimization problem. Like this. Here, so object function is a G bar W. So constructed from the validation data set. And we minimize this function with respect to the W and the hyperparameter lambda, so simultaneously. So subject to these constraints. And W must be the solution of the LQ regularized problem. So made from the GTR. And lambda is hyperparameter non-negative. Okay. So bilevel optimization problem is has a long history, but there are many abundant optimization theory and algorithm, but such algorithm is not designed to solve this kind of a problem, because this problem has a LQ regularizer. And So existing bi-level optimization algorithm cannot solve this problem. So our target is solve to this problem. Okay. Okay. So next, so I want to explain our algorithm. But before that, so let me introduce some related works on the bi-level optimization. So we are not the first, so using the bi-level optimization approach for solving the for the hyperparameter running. So bi-level optimization framework for the hyperparameter running so might be pioneered by the Bennett. And so their work does not appropriate for our problem because they assume the functions are all continuous differentiable. So, and the second one is by Kunish and Bock and Rosette. So this can be connected to our work closely because they use LQ function, so in the lower level program. So, but their theoretical analysis is limited to the case Q is 1 and 2. So this does not correspond to the case where Q is less than 1. And so I haven't yet written here. So in more recent years, so there exists popular bi-level optimization approach. So that uses a hypergradient method. But as far as we investigated, so even such a framework does not suppose solving the problem like ours. And compared with the existing works, so what is our contribution? So our contribution is summarized like this. So we present a smoothing type algorithm for solving the LQ regularized problem. So bi-level problem. So having the LQ regularized problem as a lower level problem. And one more important point is we give a convergence analysis for the case of the Q is for the case of Q less than 1. Okay, so next I want to explain our proposed method, smoothing method. Okay. Okay, let me revisit our problem we must consider. So here, so f is a continuous differential function, and g loss function, and from R to R twice continuous differential function. And this one is a non-smooth. And so denotes by capital G, so this part. And because G and Ri are all twice continuous differential functions, and capital G is a twice continuous differential function. Okay. So a natural approach for solving this problem is replacing this constraint by its first order optimality conditions. So its first order optimality condition is represented with a subdifferential, like this. So in that case, the resulting problem is written like this. But so as far as we know, so there exists no algorithm that can solve this kind of the problem. So because so there is a set value mapping constraint. So this is a very difficult. This is not tractable. Okay. So to overcome this difficulty, we use a smoothing function. So smoothing function is one of the most powerful methodologies for solving the non-smooth equation and optimization problem. That algorithm approximates the non-smooth functions by the so-called smoothing function. Okay, so in our case, we replace this function, non-smooth function, by the following function. Okay, and notice that for any mu positive, this function is C infinity with respect to W. So this figure shows graph of this function. for positive mu. So from the 1 to 0. Okay, and so the graph at the bottom is the original LQ function. And you can see as mu decrease to 0, so the graph gets closer to the original function. So but so this function is all smooth. So when mu is positive. So using this function, so our smoothing method is described like this. Sorry, so not yet. So okay, so the idea of the smoothing method is so replace this part with a phi mu. So smoothing function I said in the previous slide. And furthermore, we replace this constraint with its first order optimality conditions. So in this case, so because phi mu is smooth, so we can describe it as a nonlinear equation like this. Okay, the formal description of our method is like very simple. So we repeat these procedures. So we solve the point. So KKT point. So for each iteration, we compute a point that satisfies the KKT conditions. This for this problem. Okay, so this is all functions are smooth, and the KKT condition is so it's represented like this. So this is a bit complicated, so I don't explain here. But so this KKT condition, so the KKT conditions are very classical, but still very standard. So in fact, so most of the softwares for solving the continuous optimization, so constraint optimization problems are designed so as to find a point that satisfies the KKT conditions. So there are so many algorithms that can compute a KKT point that satisfies KKT conditions. Okay, let me go back to the previous slide. And so we compute a point that satisfies the KKT conditions of the smoothing problem. And this is a Lagrange multiplier. Okay, so zeta and eta. Then we update the smoothing parameter by decreasing mu. So beta is so positive but smaller than 1. And we update k until the convergence. So this algorithm seems to work well. So the final solution seems to have a meaning point. So have some sense. But so what kind of meaning? So in the theoretical analysis, so we clarified that point. Okay, so this is the assumption. So we assume the boundedness of the W and lambda k. Okay, and so boundedness of the Lagrange multiplier zeta and eta is also very important, but this one is can be shown under certain assumptions. Okay? So I don't explain the detail. And the second one is this kind of one. So lambda 1k, this is a hyperparameter, so correspond to the LQ regularizer is positive, so at the accumulation point. So this means LQ regularizer works effectively at the limit. So under this assumption, we proved this theorem. So arbitrary accumulation point, this sequence generated by the smoothing algorithm satisfies the bilevel KKT conditions. So what is the bilevel KKT conditions? So bilevel KKT condition is described like this. This way is a very complicated. So for example, so is a diagonal matrix, and H is defined here, and the sign is so SGN denotes the sign of the W. So I must explain. So So what these conditions are. So to explain this, so let me introduce the following problem. So this problem is obtained by replacing the original constraint with its scaled first order necessary optimality conditions. So presented by the chain and the chains group. So this condition is actually necessary optimality conditions of this first order optimality conditions. So represented with sub-differential. So this one is so as I say, this one is a necessary optimality conditions of this lower level problem. And so when Q is smaller than 1, so in fact, the converse direction also falls. So therefore, in our problem setting, so this red part and this first order optimality condition is exactly equivalent. Okay, and so what is the bi-level KKT conditions? So we prove that so bi-level KKT conditions are nothing but the necessary optimality conditions that the local optimum of this problem should satisfy. So this is our main, so second of the main result. Okay, so lastly, I want to explain the numerical experiment. Okay, so this is our experimental setting, and we implement our algorithm using the MATLAB, and we make comparison of our make a comparison of our method with a Bayes opt. So that implements the Bayesian optimization. Okay. And we use bi-level KKT conditions as a termination criteria. And so we use FMIN MATLAB solver so for solving the smooth subproblem. So and we change the smoothing parameter like this. Okay. And so we solved this kind of the problem. So based on the linear regression problem. Okay. And the data matrix and the data vector are borrowed from the UCI machine learning repository. And I use data sets like this. And feature size. So this is so the number of the variables in this program is like this. Okay. And the numerical results are like this. Here, so error bar, error test is defined like this. So error bar is a error for the validation data. So this is a object function of the bi-level optimization problem we consider here. And error test is for test data and defined like this. And W asta is the output solution by our algorithm. And this means so L0.8 and L0.5 regularizer. And also elastic net regularizer. With so Q is said to be 0.8. And M is N is a variable size, and M is a sample size for training data. So from this table, and bi-level algorithm, our algorithm, and Bayes opto is MATLAB solver. So from this table, we can see in the error test, so our algorithm is finds a better solution. So in these two cases, our algorithm is faster than the Bayes opto. And so in these two cases, we observe the similar tendency. So for the insurance, Bayes opto is a better solution with respect to error test than our algorithm. But so we think that these results are very comparative. The most important is our algorithm is much faster than Bayes opto. So students also shows a similar tendency. And as for the communities, so with N, so close to the 2000. So Bayes opto cannot find a solution within the limited time. And so our algorithm, so successfully finds a solution, but the CPU time tends to be very large. So this is because our algorithm solves a constraint optimization problem as a subproblem. so at each iteration. We also show we also make a comparison of the time and test value and validation value. So as the feature size grows. And our bilabial algorithm is it is here, so at the bottom, okay? So we can see, so our algorithm is superior to the base optimization. So in particular, so CPU time, so spend time is much smaller than base optimization. Okay. So this is a numerical experiment. Okay, so let me conclude my talk. So as a summary, so we present a smoothing type method for hyperparameter learning. Sorry, I'm sorry. And so for solving the bi-level optimization problem, whose lower level program has a non-smooth LQ regularizer with Q less than 1. And we proved so convergence to a bi-level KKT point. Okay. So we also observe the numerical efficiency of our method in comparison with Bayesian opt. Okay. So there is two directions as a future work. So one direction is to extend from our LQ regularizer to other non-smooth non-convex regularizers, such as a SCAD and the MCP. So bi-level KKT conditions can be extended to such regularizers, so by adding some assumptions. And so on the other hand, smoothing method can be straightforwardly extended to these regularizers. So actually, its convergence analysis seems very difficult. And because of the current convergence analysis, so strongly relies on the structure of the LQ regularizer. And the second direction is to consider the different smoothing function for the LQ regularizers. So recently, other research group in Taiwan pointed out, so our smoothing function here is good, but not best. So they instead presented better smoothing function, so like this. So this function, this figure shows our smoothing function, and the right side shows their other function, smoothing function, and so for the same mu from 1 to 0. So apparently, their smoothing functions fits the LQ regularizers more. So perhaps using these functions may improve our algorithm further. So this is the ongoing work with Taiwan's research group. Okay, so that's all. Thank you for your attention.
For next, we have seminars, so please join a seminar from next week again. And so yeah, thank you for attending this seminar. Thank you for giving questions, and I hope you notice our research group activities. So thank you guys, and also speakers, the person who gave a question, and all attendants. Thank you so much. Bye.